So this section is about Venn diagrams, and Venn diagrams are used to organize data and to show relationship between sets. Okay, so there are a couple of steps to drawing a Venn diagram. So the first step here is draw an outer box to represent the universal set S. So that's this outer box you see here. S represents our universal set. And step number 2, inside the box, we're going to draw some overlapping circles to represent groups of items or our set of items. So you can see already in our first Venn diagram down here is a circle for set A and circle for set B, and then they overlap. So the items in a set are called the elements or members of the set. And the size of the circles does not have to be proportional to its elements. It can be any size, big, small. Okay. And any overlap will designate common elements. If all elements of one set are in another set, it becomes a subset. Okay. So when you have two sets here, A and B, and when they overlap each other like this, the elements that they have in common are in this what we call the intersection between the two sets. And so we have a special notation for that, and it's this symbol right here. It looks like an upside down U. It's a little bit wider, so it's a wide U that's upside down. Intersection of sets. So this is a subset, and it contains elements that are common to all sets, so in all the sets that are intersecting. Okay, and so to show that, we say that A intersects with B, like so. Okay, so that's the first kind of set that we're going to encounter. Then you have a union of sets, which looks like a very wide U. And a union of sets, when you have two overlapping Venn A and sets A and set B like this, what we refer to is just not the overlap, but the entire thing. We're joining both all the elements from A and all the elements from B to make this union. Okay, so the union of sets is distinct elements that belong to the collection of sets. Okay, and we denote this with a wide U, so we can say here for this Venn diagram, A is in union with B. Okay, now each element has each set has its intersection, so you might think, oh, if the elements was in A as well as the elements are in B, then you're double counting them. Well, and when you're joining the sets in union, you can only count the intersection once. So when I say distinct elements, so distinct elements, you count the intersection only once. Okay, and then we have our disjoint sets. So disjoint sets are sets that have no common elements. Okay, meaning there is no overlap. So whatever elements I have in A, they are separate from all the elements that I have in B. Okay. So as it can be seen, Venn diagrams can be very useful when we want to know the number of items in a category, especially when there is an overlap between different categories. So here's a question. If A and B are disjoint, just like you see up here, how does the number of elements in the A union of B relate to the number of elements in set A and the number of elements in set B? Okay, so A union B will be the sum of A and B, meaning all the all the elements in A and all the elements in B. I'll add them together to make this union of A and B. Okay. So in general, for disjoint sets A and B, the number of elements n in the A union B is equal to the number of elements in A plus the number of elements in B. Okay, and this is only for disjoint sets, because if it were a joint, then you'd have some overlapping elements, and this would not work. Okay, let's go down to an example in drawing some Venn diagrams. So when TDSS first opened with grades 9 and 10 only, there were 240 grade 9 students enrolled and 218 grade 10 students enrolled. So use a Venn diagram to illustrate the total number of students enrolled at TDSS when it opened. Okay, so let's call the first set the set of grade 9. So let's say A is equal to the set of grade 9, and we'll say B is the set of grade 10. Okay, so in my diagram, I'm going to have so let's draw a nice circle here. So let's just use my tools and create a nice circle. Boom, here's my circle for set A. Here's another circle for set B. Again, the sizes don't matter. Okay, we know A is bigger, so I'm going to say, let's say this one is A. Oops, let me go back to the pen. So here we go. Let's say this one is set A, and this one is set B. Okay, and so in set A, the grade 9s, we have 240 of them. Set B, we have 218 grade 10s. So how many total number of students do we have here? So we're going to say the union of A and B is equal to the number of elements in A plus the number of elements in B. Okay, and that's equal to 240 plus 218, and that's equal to 458 students. So therefore, there were 458 students enrolled. And for the moment, I just lost my numbers here, so let's just put them back in there. And B is 218. And the whole Venn diagram, this is my sample space, and in total we have 458. Now notice this, the two sets are not joined, okay, and they are disjoint, and it makes sense when you look at the problem. And this is what you have to sometimes analyze: are the diagrams going to be joined or disjoint? And these are disjoint because grade 9, if you're a grade 9 student, you can't be in grade 10, and if you're a grade 10 student, you can't be grade 9. So there's not going to be any overlap. Okay. So that's the next question. What if the sets A and B are not disjoint? Then how does the number of elements in the union of A and B relate to the number of elements in set A and the number of elements in set B? So let's look at another example. So in example number 2, there are 10 students on the volleyball team and 15 on the basketball team. When planning a field trip with both teams, the coach must arrange transportation for a total of only 19 students. Okay, explain why the coach isn't arranging transportation for 25 students. Okay, and it turns out, there are, these are not distinct students. There's some students who play on both the volleyball team and the basketball team. Okay, so I'm going to say here my explanation is that there are some students who play on both teams. Okay, all right, we determine how many student members are on both teams. So if you have a total of 25 students, but you're transporting 19 students, then if we subtract the difference, then that means 6 students must be playing on both teams. So it's just logic. Okay, so 25 students is what you'd have 10 plus 15 if we were disjoint, but because the coach is only busing 19 students, that means that difference must mean that those 6 students must be playing on 2 teams. It's the only way you can account for the fact that a transportation for only 19 students takes care of both of your teams. So part C, use a Venn diagram to illustrate the situation and determine the number of students in the remaining regions of your diagram and explain what these regions represent. So let's just draw a Venn diagram. Okay, so here's a little box. So we start with the box. I'm going to draw two circles. So here's one circle here, and here's another circle here. Okay, and maybe I can make that a little bit bigger. So let's see if I can click that, make this a little bit bigger. Okay, maybe I can click on this and make this a little bit bigger. Okay, and a little more overlap to show there. Okay, perfect. So I'm going to say here that we have a sample size of 19, so S equals 19, and we have a volleyball team and we have a basketball team. Okay, so it's the number of people, the students that are in both teams is 6. Okay, so how do I figure out the numbers in each? Well, it turns out the number of people in our volleyball team minus the intersection, so the number of people in our intersection, will give us the number of individuals of the students that are only in volleyball, right? So the volleyball team is composed of 10 students, and I subtract the intersection of 6, it leaves me with 4. So there are 4 students in this part of my Venn diagram, 4 students who are exclusively in the volleyball team only. Okay, and then there are 6 more that make up the volleyball team, but these 6 are also in the basketball team. Okay, so then how many make up the rest of the basketball team? So the number of people on the basketball team minus the number of people in both teams give me the number of students that are exclusively in the basketball team. So the basketball team has 15 members, subtract the intersection of 6. That means there are still 9 players that are part of the basketball team, but not the volleyball team. Okay, so my conclusion is 4 play just volleyball. Why is it stuck? Okay, 4 play just volleyball. 9 play just basketball. And there are 6 students who play both. Okay, so if you look closely, well, 9 plus 6 is 15, so you need 15 for the basketball team, which is what we had up here. And then 4 plus 6 is 10, which is what you have up here. 10 students play volleyball. Okay, so principle of inclusion and exclusion for 2 sets. So for 2 sets, A and B, the total number of elements in either A or B is the sum of each set minus the common elements in both. Okay, so for sets A and B, the total number of elements in either A or B is the sum of each set minus the common elements in both. That makes just sense, right? So if you have 2 sets, A and B, they have a number of elements in A, a number of elements in B, minus the intersection of both, because you don't want to double count the intersection. If you add up all these numbers up, you'll get the union, the number of elements in the union of A and B. Okay, so this formula here is for when you have an intersection. These are not disjoint sets, and the formula you have all the way up here is the number of elements when you join 2 sets A and B, but the sets themselves are completely separate, like you have in this Venn diagram. Okay, they're disjoint sets. But when you have a joint set, you also have to subtract the intersection, so you don't double count. Okay. So the principle of inclusion and exclusion for 2 sets can also be applied to 3 or more sets. So how would that look like? Well, if you had 3 sets, it looks something like this. So let's just draw some circles here, and one more. I gotta move this one. Let's see the tool here. Let's move this. Okay, and I'm going to move that in there. Oop, what did happen? Stylus pen. That's fine. Okay. Let's move this all the way over here. And there you go. Okay. And so I have here a set A, and B, and C. Well, it turns out the union of A, the union of A, B, and C is equal to the number of elements in A plus the number of elements in B plus the number of elements in C, but you also have to subtract all those intersections, because you keep in mind that this part here is an intersection of A and B. This part here is the intersection of A and C, so you don't want to be double counting that. There's this part here is the intersection of B and C, and then don't forget you could end up again double counting the intersection of A, B, and C. Okay, so you have to subtract the number of elements in the intersect of A and B, subtract the number of elements in the intersect of A and C, and you have to subtract the number of elements in the intersect of B and C, and then but don't forget, every time you're subtracting like A and B, well, you're subtracting this portion right here, so you're subtracting the middle. Every time you subtract the B and C together, you're also subtracting the middle again. And every time you take care of the intersection of A and C, you're subtracting not only this part, but also the middle. So you've completely gotten rid of the middle 3 times. Okay, so you have to add it back in. So add 1 time the that intersection. So you add the intersection of A and B and C. That's why this is plus over here. Okay. All right, let's look at another example. Example number 3. An advertising company is researching the effectiveness of their credit card ads. They surveyed 250 people who owned a Visa card and 180 with a MasterCard. If 72 people have both cards, how many people were surveyed? So we're looking at the total number, the union of the number of people who have Visa cards in union with the number of people who have MasterCards. And so that's going to equal the number of people with Visa plus the number of people with the MasterCards minus the number of people who both have a Visa and a MasterCard. Okay. So we know that 72 people have both cards. So we have 250 people who have Visa plus the 180 who have MasterCard minus the 72 who have both, because you don't want to double count those people. So the total number of MasterCards and Visa cards holders out there is going to be 358. Okay, so therefore 358 people were surveyed. Okay, part B, use a Venn diagram to calculate how many people have only one of the 2 cards. Okay, so how many people have only one of the 2 cards? So we know if you want to know how many have Visa only, well, that's going to be the number of people who they had declared had Visa minus the number of people who claim to have Visa and a MasterCard. So you don't want to include those who have a MasterCard, even though they already have the Visa. So we have 250 people on the survey who said they had a Visa, but you also have to take away the 72 people who said that they had a MasterCard as well as their Visa. So that's going to be a number of 178. Okay, same idea for the MasterCard only. So that's going to be the number of people who have a MasterCard minus the number of people who have both a Visa and a MasterCard. And if I write the answer here, that's going to be 180 minus 72, which is 108. And now I have the numbers I need to complete my Venn diagram. So the sample space here is 358. Total people were surveyed. Just going to draw my 2 circles. So here's one, and here's another. And I'm just going to move them a little bit closer together to each other like this, just so as you can see a good intersection here. Oops, that's too much. Let me just tone it back a bit. There we go. Okay, so I'm going to say the left one is the Visa holders, the right one is the MasterCard holders, and inside I have 178 who own Visa and only a Visa, And on the right, I have 108 who only own a MasterCard, and in between, I have the ones who own who share both, 72. Okay. All right. So actually, when you're doing Venn diagrams, I think the proper thing to do is just to make sure you put V and M on the insides of your set. And I can make the same corrections up here. Let's put V on the inside, or B. Okay. All right. So example 4, of the 350 grade 12 students at TDSS, 89 have signed up for calculus, 104 for advanced functions, and 75 for data management. Of these math students, 14 are taking both calculus and functions, 20 are taking both calculus and data management, and 24 are taking both functions and data management. Only 6 are taking all 3. How many students are not taking any of these 3 math courses? So now we have 3 sets to consider. So we have C for calculus, and we have, we'll say D is for data management, and we'll say F is for functions, advanced functions. Okay, so the union of C, D, and C, D, and F, well, that's equal to the number of students in calculus plus the number of students in data management plus the number of students in advanced functions. But you also have to subtract their intersections. So minus the intersection of calculus and functions, minus the intersection of data and functions, and then minus the intersection of what am I missing here? Calculus and data. So calculus and data. But by doing so, you remove the middle portion of those 3 intersections of those sets, and so you have to add that back in, add the intersection of all 3. So add the intersection of C and D and F all together. Okay, so we know the number of students who have signed up for calculus are 89, number of students who signed up for data is 75, and number of students who signed up for functions is 104. But 20 signed up for, how many? So 20 or 14 signed up for both calculus and functions, so minus 14. You have to subtract the number who signed up for data and functions, which is 6. Oh no, not 6. It is 24. Data and functions is 24. And subtract the number who are taking both calculus and data, which is 20. Then you add back the 6 who are taking all 3. So in total, there are 216 students taking all 3 courses. Okay. And so out of 350 students, if you take away the 216 taking the math courses, then there are 134 students taking no math courses. Okay. Part B, illustrate the course enrollments with a Venn diagram. So here in my Venn diagram, I got to know how many students are taking calculus only, functions only, and data only. Okay, so calculus only is equal to the number of students taking calculus minus the number of students taking both calculus and functions. I have to write the sign here, so calculus and functions minus the number of students taking calculus and data plus the intersection of all 3, so calculus and data and functions. Okay, so that's equal to the 89 who signed up for calculus minus the ones who signed up for data, functions, and calculus minus the ones who signed up for calculus and data plus the 6 who signed up for all 3. And so that gives me a total of 61. Okay, functions only. So the number of students who signed up for functions, take away the students who signed up for both functions and calculus, and take away the students who signed up for both functions, and, functions, and, calculus, and take away the students who signed up for both functions and data, and you add back in the intersection of all 3. So and we're going to get an answer of, well, let's do the numbers. 104 minus 14 minus 24 plus 6 is equal to 72. And then the data only, the number of students who took data minus the number of students who took both calculus and data minus the number of students who took functions and data plus the number of students who took all three. And so that's going to equal 75 minus 20 minus 24 plus 6, and that is 39. So now I have the numbers I need to fill in my Venn diagram. So calculus, functions, and data. Okay. Sample S is 134 outside this set who do not have, we're not taking these math courses. And so I know I have 61 who taking calculus only, I have 72 taking functions only, and I have 39 taking data only at this school. Okay, what about the other numbers? If I go back up here, you can fill in the rest. So 6 are taking all three, so right in the middle goes 6. And then we have 14 taking both calculus and data. And then we have 8 who are taking calculus and functions. And we have 18 taking both data and functions. Did I make a little error? Whoops. Okay. Nope. No. So data and calculus and data, 14 plus 6 make up the 20. Calculus and functions, so 8 plus 6 make up the 14. And then functions and data, well, 6 plus 18 make up the 24, taking both functions and data. Okay, and so that's how we create this Venn diagram when we have three different sets intersecting. And don't forget, 134 students are not taking math courses, so this is what goes on the outside.